To the first lesson of Chapter 5 in Calculus. I hope the substitute has handed out your note packets. We're going to review how to differentiate a natural log function. Before we go too much in depth, we need to remember what logarithms actually mean. Back in Algebra 2 or pre-calculus, we would have reviewed that b raised to the k power equals n is like saying log base b of n is k. So that's all this is saying, is that if you have the logarithm of n with the base of b, it's saying that b raised to whatever power gets me n. Logarithms are just exponents. All the properties of exponents are the properties of logarithms and vice versa. This natural logarithm function, ln of n, would mean that we have a log with the base of e, which is the natural number, Euler's number. And e, if you recall, is around 2.718. And it has the unique property that the derivative of e to the x is just e to the x. And consequently, du of e to the u, with respect to x, d dx, e to the u is e to the u times u prime. When we attempt to integrate something like this, 1 over x dx, we have a problem. X to the negative 1 dx, we use the general power rule, we get x to the 0, and that's not the problem, because I have to add 1 to the exponent, and then divide by whatever that exponent was. It's dividing by 0, that's the problem. You're going to have a bad time. Don't divide by 0. So then we found this unique relationship that the integral of 1 over x dx is equal to the natural log of x plus c. And the derivative, then, of the natural log of x is equal to 1 over x. And consequently, we'll learn on the next couple slides that the derivative of x of the natural log of u is being u prime over u. Properties of the natural logarithmic function. The domain is 0 to infinity. Think about that. The x values, the domain, is 0 to infinity. That's because the natural logarithm function looks something like this. So I can only have x values that are positive, and the y values can be whatever I want them to be. The function is continuous, increasing, and 1 to 1. That means that for every 1 to 1 means that if you have f of a equal to some other f of b, that implies that the a value is equal to b value. That means that there's no repeating function values. That means if you have a function value, so let's say f of x is 2, then x will always have to be the same. It's never going to hit 2 again. In a simpler way, if you're still confused, think of it this way. If a function is 1 to 1, that means if I have a horizontal line, that means it's never going to touch the horizontal line more than once. And that's very important for finding inverses. And of course, the inverse function of the natural log function is e to the x, which is why we have this really interesting relationship between the derivative of natural log and 1 over x. The graph is always concave downward, which means that the second derivative is always what? Less than 0, negative. Hope I almost forgot one other part. What does it mean it's always increasing then? First derivative is always greater than 0. Here are some interesting properties of logarithms you should remember. The natural log of 1 is 0, because that just means that the log base e of 1 has to be x. So if e to the x has to be 1, the only way that's possible is when x is 0. So that's why the natural log of 1 is 0. The natural log of a times b is just the natural log of a plus the natural log of b. This is an exponent rule, remember? When I multiply by the same base, you add the exponents. Now this is the same base of e, okay? So you add the exponents. Natural log of a to the nth power, remember you can just move that a out front, or that n out front, n times natural log of a. Natural log of a divided by b is natural log of a minus natural log of b. Exponent rules. Now, we're not going to do any calculus here. This is just algebra 2. We'll just expand these expressions just so you get the hang of these properties. If I have the natural log of the quotient 12/5, that's going to turn to the natural log of 12 minus the natural log of 5. So when I divide by the same base, you get the same. Subtract the exponents. The natural log of the square root of 2x minus 1 is like the natural log of 2x minus 1 raised to the 1/2 power. Move that 1/2 out front. 1/2 the natural log of 2x minus 1. All right. We have the natural log of 3x over 7. It means I'm going to have the natural log of 3x minus the natural log of 7. And notice I have the natural log of 3 times x, so I can expand that even further. The natural log of 3 plus the natural log of x minus the natural log of 7. Over here we have a more complicated one, so we'll first do the quotient. Natural log of x squared plus 2 to the 3rd power minus the natural log of 4x. We're going to bring that 3 down. We have 3 times the natural log of x squared plus 2 minus the natural log of 4. And again, I can separate the 4x out into natural log of 4 and natural log of x. Notice I'm subtracting both of them. Plus sign there. I could separate out this natural log of x squared plus 2. Oh, I can't do that actually. Why can't I do that? I'm not multiplying these two, so it has to just stay the natural log of x squared plus 2. This is not a product. I cannot expand that. But I can distribute the negative sign to both the natural log of 4 and the natural log of x, and then we're done. The base of natural logarithm is defined using the fact that the natural logarithm is continuous 1-to-1 and has a range of negative infinity to positive infinity. So there is some value of x such that the natural log of x equals 1 and this base is denoted e. The natural log of e is 1. I've already decided that. So in summary, the derivative of the natural log of x is equal to 1 over x, and in general, the derivative of x of natural log of something, u, is 1 over u times the derivative of u with respect to x. In other words, in your textbook, u prime over u. The derivative with respect to x of the natural log function evaluated at u is u prime over u. Find the derivative for each. So, in this case, I have the natural log of 2x. Now this, I don't have a derivative rule for the natural log of 2x. I do have a derivative rule for the natural log of u though. So if I let u be 2x and du would be 2 times dx, right? So that means the derivative of u with respect to x, so du dx, is equal to 2. This is also the same thing as u prime. Then the y prime of this expression will be u prime over u, which is the same thing as 2 over 2x, which is just 1 over x. Going over here, u is equal to 2x to the 3rd plus 5x. Now we're kind of have to get out of the habit of doing u substitutions. We're just doing it for integration, that is. So we're just doing a u substitution for derivatives. This becomes 6x squared plus 5. So then f prime of x is going to be u prime over u, which is the same thing as 6x squared plus 5 over the u, which is 2x to the 3rd plus 5x. Remember, there's no plus c because I'm not integrating. Now, actually, I was just in a habit here. You don't even need that. What's going on in this problem? It's been a while since we've done this. What are we doing? Product rule. Okay, so y prime then is going to be left d right. Remember, left derivative of the right with respect to x plus the right times the derivative of the left with respect to x. So the left is 3x to the 5th. The derivative of the right is 1 over x times the derivative of x, which is 1, plus the natural log of x, the derivative of the left, which is going to be 15x squared. So I get 3x to the fourth plus, looks like 15x squared natural log of x. Now, sometimes we use logarithmic properties to help us with differentiation. So in this case, I have f of x is equal to the natural log of the cube root of 3x minus 2. So we can help ourselves out by just rewriting that this is going to be 3x minus 2 to the 1/3 power. And because I'm taking the logarithm of that whole thing, I can move this exponent down to the front. That's going to make taking the derivative a whole lot easier. Because now f of x is actually 1/3 the natural log 3x minus 2. Of course, when you take the derivative of that, the 1/3 doesn't really matter anymore. So the 1/3 just kind of goes out front there, and I just take the derivative of this, which of course is u prime over u. So it would be u prime is just 3, u is 3x minus 2. Of course, 3's cancel out, you just get 1 over 3x minus 2. On occasions, it is convenient to use logarithms as aids in differentiating non-logarithmic functions. This procedure is called logarithmic differentiation, and this is something that's going to be very useful to you in the future. If you can't quite take the derivative of something easily, try to see if you could use logarithms to help you out. Now, f of x is equal to the square root of x squared minus 1 over x squared plus 1. And it says that x has to be greater than 1. That's super important if you want to use logarithms, because of course you can't take the logarithm of anything equal to 0. So if x is bigger than 1, that's going to be helpful to you. F of x can be written as the quotient x squared minus 1 over x squared plus 1 raised to the 1/2. Now if I take the logarithm of both sides, the natural log of f of x, and that's going to be the natural log of the right side too. So basically in this step, all I've done is take the natural log of both sides. Now I can move that here, and I'm going to change f of x to just be y, just to keep it simpler for myself. And move that 1/2 over, and I have the natural log of x squared minus 1 over x squared plus 1. And now I can separate that logarithm out on the right side, be 1/2 times the natural log. And what happens when I have a quotient? What do? Subtract. Of course, this 1/2 is going to be multiplied by the entire thing. Natural log of x squared plus 1. And so now, if I want to take the derivative of both sides, if I have the derivative of something other than x, this is basically my u now. My u is y. And du dx would be y prime, or the derivative of y with respect to x. So then the left side becomes y prime over y. And actually, I'm just going to use purple again. Is equal to, and if I take the derivative of the right side, the 1/2 can be distributed to everything. So I have 1/2 the derivative of the natural log of this, and then the u substitution for this one's going to be different. In this case, u is x squared plus, keep messing that up, x squared minus 1, du dx would be 2x. So this is actually u prime. Remember, I use the expression du dx for when we do integrals, but now that means that the derivative of the natural log of x squared minus 1 would be u prime over u, so it would be 2x over x squared minus 1. Minus, and then that 1/2 also comes from the beginning again, and this u would be yet another different u, so u would be x squared plus 1. U prime would be 2x, so it would be minus 1/2 of 2x over x squared plus 1. And of course, you could simplify this more. You have to multiply both sides by y. I'm just running out of time on this video. So it's going to be x over x squared minus 1 minus x over x squared plus 1, and that whole side has to be multiplied by y. which is the original function. So just remember,